Hi everyone, welcome back to 3 Deviations. In today's video, we want to cover another important vector product called the cross product. So in the last video, we covered the dot product. Now the dot product was also known as the scalar product, and there was a very nice way of defining that in terms of index notation, such that we could define it as the sum of multiplying the corresponding components of two vectors, or multiple vectors, however we want to do that. Anyways, the cross product is also called the vector product. Now, it's called the vector product because it produces a vector, not a scalar. So the result of this vector will be, the result of this product will be a vector that is perpendicular to both vectors A and B in three-dimensional space. Okay, now why don't we cover the cross product now in abstraction? Now, this looks quite complicated, but I will walk us through it. Now, given A and B, three-dimensional vectors, then we can say that A times B, or A cross B, is equal to the vector with the components A2, B3 minus A3, B2, A3, B1 minus A1, B3, to A1, B2 minus A2, B1. All right. Now, this is obviously something you can just memorize, but we also want to drive it into possibly more compact ways that will make it easier to remember. Now, one of the things you might notice if you have taken pre-calculus is if you have the 2x2 matrix, A, B, C, D, and I want to take the determinant, so if that's matrix A, if I want to take the determinant of that matrix A, that is equal to AD minus BC. Okay, now why is this important? Well, what we actually see at this point is a series of determinants in our vector. So A2B3 minus A3B2, that looks like the determinant of a matrix, right? So what we can say is that we can set our cross product also equal to the determinant of the matrix I hat, J hat, K hat, A1, A2, A3, B1, B2, B3. And the way that we take the determinant of this 3x3 matrix is, I believe it's Cramer's rule, possibly, but anyways, you will look that up. I didn't write it here, but basically you take the determinants of, you take the determinant of this matrix, and then you associate it with this, then you take the determinant of the second, or the first row and the third row, you associate it with this one, and then you do this matrix, and you associate it with that one. There's basically kind of a cross action in there, so we can call that the cross product. Now the final vector is going to be orthogonal to A and B, so this is a vector that's perpendicular to both A and B, and that is how the cross product works in abstraction. Now we can try an example so that we know what we're doing. I'd like us to compute the cross product of the two vectors A and B, such that A is equal to 156 and B is equal to 524. All right, so what we do is we're going to plug this into the, oh wait, actually, these are the wrong vectors. I will rewrite them. A vector is going to be equal to 1, 3, 4, and B vector is going to be equal to 2, 7, negative 5. Right, anyways, we put that into our matrix. Then we use our rule for the determinant of the 3x3 matrix. We get determinant of 3, 4, 7, negative 5 I hat minus the determinant of 1, 4, 2, negative 5 j hat plus the determinant of 1, 3, 2, 7 k hat. Now what we do is, again, we use the rule such that the determinant of a 2x2 matrix A, if A has elements A, B, C, D, this is equal to AD minus BC. And thus we get the vector negative 43, 13, 1. This is a vector that's perpendicular to both A and B, such that A and B are the vectors that we've got up in there. Right, now similar to the cross product, or similar to the dot product, we have a cross product analog with the trigonometric idea. So we can determine an angle between two vectors A and B. We call that angle theta. If we can find that angle, we can find the dot product, because the dot product is equal to the magnitude of A times the magnitude of B times the cosine of that angle between them. Now, the magnitude of the cross product, now notice we need to do the magnitude of the cross product because, of course, the cross product would be a vector and our analog would produce a scalar. So the magnitude of the cross product A times B is equal to the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. And now we can look at some of the properties of the cross product. These properties are also going to use the dot product a little bit. The first property states that if I take A cross B, that's equal to the negative of B cross A. That's a little bit different from the dot product. It's very important now that we have a vector quantity being produced. If I have a scalar multiplication, so D times A cross B is equal to D times A cross B, so we have a distribution property there. Okay, also, if I take A cross B plus C, then I can distribute the A, so I get A cross B plus A cross C. Furthermore, if I do the same thing but from the right hand, I can also use the distributive property, but of course C will go on the right hand side. Obviously it's very important our order because we have this anti-commutation there. Okay. Fifth, we have the rule that if I dot A with B cross C, then that's equal to A cross B dotted with C. Finally, if I take A cross B cross C, then that's equal to A dot C times B minus A dot B times C. All right, so those are the properties of the vector product or the cross product. Now we have an application. If I want to find the volume of a parallelepiped created by two vectors in three-dimensional space, or three vectors in three-dimensional space, A, B, and C. So A, B, and C, if I have a vector A, if I have a vector B, and I have a vector C, these are going to make a parallelepiped in three-dimensional space. So if I have something like this, and I'm extending this a little bit for the sake of our ability to see things here, but I will get a parallelepiped like so, or a prism of sorts. This will be a three-dimensional object, and essentially, if I want to find the volume of this, then I can use the following formula, such that I take volume is equal to the magnitude, obviously because we want a scalar quantity, of a vector A times B, or dotted with B cross C. All right, and finally we've got an application here for torque. So torque is a quantity in physics. It is in rotational physics. It has analogs to translational physics as well. Anyways, the vector torque is equal to the position vector crossed with the force vector. Let's say a bolt is tightened by applying a force of F newtons to a wrench of D meters. Find the magnitude of the torque about the center of the bolt if the force is applied at an angle theta degrees off from the wrench. So if I have a position vector R, that's my R, or that's my D, I guess, then my force is there, and then and then I have a theta off of the diagonal, and then there's our bolt. Well, then I can use the relationship for torque and the angle between our two vectors, such that the torque is equal to the magnitude of the force times the magnitude of the distance times the sine of theta. All right, thanks for watching today's video. In the next video, we're actually going to be moving on. We're going to start talking about lines and planes in 3D space. And after that, we are going to be talking about how we can use our knowledge of the conic sections to build some so-called conic sections for three-dimensional space, which will be very helpful in the future. All right, thanks for watching. We'll see you in the next one. Bye.